In this video, I'm going to talk a bit more about these coordinate transformations. So what I have here is our original coordinates, the x-axis and the y-axis, and it is being transformed so that it rotates this way by theta degrees, so that we have our x prime here and our y prime here. And I am going to say that theta is equal to 45 degrees. This is about 45 degrees. I'm just going to say close enough. And so what we want to do is first look down here at these are our bases here. In black are the bases for the original coordinates, and then in blue are for the rotated ones. And so I am going to define these in column vectors. And so we will say that E1 is equal to 0, 1. And so this is the column vector. So there are two elements in it because we have a two-dimensional plane here. The top one is the y-axis. So it's how much y something has, how much it is sticking into the y direction in either way. If it's up, then it would be positive, down is negative, but since E1 is only pointing in the x direction, it's 0, and it has 1 going in the x direction, which is this bottom number. And so then this will be the opposite, where it has 1 going in the y direction and has no component going in the x direction. And so now what we want to do is figure out what our E1 prime is and our E2 prime. So we want to figure out in terms of the original coordinate system what the new bases are. And so I talked about in the previous video that to perform a rotation we will use a matrix that looks like this. So cosine theta, sine theta, negative sine theta, and cosine theta. So that is our transformation matrix. And since I've said that theta is 45 degrees, we can look over here at our unit circle, and 45 degrees is this. So cosine and sine of 45 degrees are both the same thing. So I'm going to call it 1 over the square root of 2. It's the same thing as this. You can see if you just multiply it by square root of 2 over square root of 2 that you get square root of 2 over 2. But I'm going to use this because that is the version of it that is used in quantum mechanics, which is where this stuff is eventually going to be going. And so we can now substitute each of these elements in the matrix for those identities over there. So we have 1 over square root of 2, 1 over square root of 2, negative 1 over square root of 2, and 1 over square root of 2. And so that is our matrix. And now what we can do is multiply this by our basis vectors. So the column vectors that I use for the basis vectors. So the E1 was 0, 1. So for this, what we can do is just multiply it out. So 1 over square root of 2 times 0 is 0, and 1 over square root of 2 times 1 is 1 over square root of 2. And then for the bottom number, we have negative 1 over square root of 2 times 0 plus 1 over square root of 2 times 1. And so we have this, which is going to equal 1 over square root of 2, 1 over square root of 2. So this is the E1. This is the this blue one right here, basis vector. So we know that this one is is 1, 0. This is 0, 1. This one will be the 1 over square root of 2, 1 over square root of 2. And you can see how that kind of makes sense, because if we have a basis vector that goes, we'll say that it maybe goes out to right about here, so it's the same length as the basis vectors from the original coordinates there. And so this we can see goes down there, goes up, goes to there, and those will be at 1 over square root of 2 and 1 over square root of 2, which is well, it's a little bit more than half, because you can imagine 1 over 2 is half, and square root of 2 is less than 2, so 1 over square root of 2 is going to be greater than 1/2. And that makes sense that you can see it kind of going a little bit further than 1/2 there and further than 1/2 there. And we will do the same thing for our E2 up here. So we will have 1 over square root of 2, 1 over square root of 2, negative 1 over square root of 2, 1 over square root of 2. And now we are multiplying it by this column vector, the E2 column vector. And for that we'll get 1 over square root of 2 times 1 is 1 over square root of 2, plus 1 over square root of 2 times 0, so that's 0. Negative 1 over square root of 2 times 1 is negative 1 over square root of 2. 1 over square root of 2 times 0 is 0. And so we end up with 1 over square root of 2 and negative 1 over square root of 2. And we can see that this makes sense too, because our y component is still positive. If we go back to this, so now this is our new basis right here. And so we can see that the y component here is still positive. It's still sticking this way. But now the x component is negative, and it's negative 1 over square root of 2 because it's pointing to this quadrant here. And so it's negative, and that makes sense for this, that this would be a positive 1 over square root of 2 and this a negative 1 over square root of 2. And so we can also look at this idea of what's called the identity. So identity. And this is just a matrix that will give you back exactly what you had. And I'll just say right now that it's going to be 1, 0, 0, 1. Because if we multiply this by 1, 0, then we will just get 1, 0. And if we multiply it by 0, 1, we will just get 0, 1. And we can check this too by essentially you do a rotation on one of these and then rotate it back. And to do that, you just take, so we have our cosine of theta, our sine of theta, our negative sine of theta, and our cosine of theta. And then we will just multiply this by the matrix that would move it back to where it originally was. And that would be cosine of theta minus sine of theta, sine of theta, and cosine of theta. And for this, what you will end up with if you multiply it out, I'm not going to go through the whole process. I'll just write down what I've already done here. So cosine squared of theta plus sine squared of theta for our first element Then we have negative cosine of theta times sine of theta plus cosine of theta sine of theta for our next element. Then this one down here is negative sine of theta cosine of theta plus cosine of theta sine of theta. Then over here we will once again have sine squared of theta plus cosine squared of theta. And this will be the new, well, it's multiplying both of these matrices together. And we can see pretty easily that this is going to be 0. This is going to be 0. And if you remember your trig identities, cosine squared plus sine squared, regardless what order it's in, equals 1 and equals 1. And so we end up with that identity matrix. And so we can think of the identity matrix kind of like this as sort of performing a rotation. So if we have axes here, then we rotate it to here with the first matrix. Then the second matrix is just going to rotate it right back to where it started by doing this inverse matrix. And so, well, I don't know if I want to call it inverse matrix. So it's the reverse matrix. Well, it's the transpose matrix, and so we just kind of switched the signs in the off diagonals here. So the negative sign went from here to up here, and that is how we ended up with these two matrices. One that one that moves it in this direction, and then one that moves it right back in the other direction. So if we want to generalize this, then we can go back to using, instead of using these identities, we'll just use, so cosine of theta here, sine of theta here, negative sine of theta here, and cosine of theta here. And if we multiply this by our 0, 1, which was the E1, if we look back here, the E1 was the 0, 1 column vector. And so for this, what we will get is cosine times 0 equals 0, and then sine times 1, so plus sine of theta. And then for the bottom one, we have negative sine times 0, so 0 plus cosine times 1, so cosine of theta. And so we end up with the general general column vector here for our E1, so for E1 transformations. And then if we do the same thing, so cosine theta, sine theta, negative sine theta, and cosine theta, and multiply that by 1, 0, so by our E2, then what we get is cosine times 1, which is cosine of theta, sine times 0, so plus 0, and we get negative sine times 1, so negative sine of theta, and then cosine times 0, so plus 0. So the general column vector for E2 is cosine of theta and negative sine of theta, which we can see makes sense for this over here as well, because these were all positive, and then this one down here turned negative, and that's what we have going on here. And so that is the more general way of talking about these transformations here. And just to sort of recap, we had our transformation matrix here, which is just rotating our coordinates about the axis. It's just sort of a rigid rotation about the axis. We're not moving the axes independent of each other so that we end up with, something like this, with axes that look like this or this. We are just rotating the axes so that it's something like this. They remain 90 degrees from each other. But it is possible to rotate just a single axis. Yeah, I guess I'll go through that just real quick here. We can imagine that that if we have our transformation matrix and we want to, let's say that we want to leave that one as it is, but then move the y-axis so that it's like this. Well, then we know that that our basis vector for the x-axis, E1, is going to just remain the same. And so to do that, if we have I'm just going to use CS minus S and C just to keep things quick here. So our C times 0 is 0, and then our S times 1, so plus S, then our negative S times 0, C times 1, so 0 plus C. So we know that what we're going to want is for this S and this C here to remain constant. So we want this to be sine of 0, which equals 0, keeping that at 0, and we want this to be cosine of 0, which equals 1, keeping those the same. While these two here could then transform the y-axis, and so if we have our E2 here, which is 1, 0, and we have our transformation matrix like this, then we want our C times 1, so C plus 0, and then our negative S, so negative S plus 0, and we want this C to equal, so whatever degrees we are changing this. And so that is how you could transform one of these axes while keeping the other one the same. I hope this was somewhat enlightening, and maybe this helped these concepts make a little more sense to you. I will see you in the next video.